On March 18, 2011, the Messenger spacecraft entered orbit around Mercury to become that planet's first orbiter. The spacecraft's instruments are making a complete reconnaissance of the planet's geochemistry, geophysics, geologic history, atmosphere, magnetosphere, and plasma environment. Carnegie scientists Sean Solomon and Larry Nittler, along with Brett Denevy and Ralph McNutt of Johns Hopkins University's Applied Physics Laboratory, are among researchers evaluating a wealth of new information and surprises. Images obtained with Messenger's Mercury dual imaging system are being combined into maps for the first global look at the planet under optimal viewing conditions. New images of areas near Mercury's North Pole orbital show that region hosts one of the largest expanses of volcanic plains deposits on the planet, with thicknesses of up to several kilometers. The images confirm that volcanism shaped much of Mercury's crust and continued through much of Mercury's history, despite an overall surface contraction that tended to inhibit the flow of volcanic material onto the surface. Among the fascinating features seen in flyby images of Mercury were bright patchy deposits on some crater floors, but they remained a curiosity. New targeted dual imaging observations revealed them to be clusters of rimless irregular pits with horizontal dimension from hundreds of meters to several kilometers. The etched appearance of these landforms is unlike anything seen before on Mercury or the Moon. The X-ray spectrometer has made several important discoveries since orbit insertion. The magnesium-silicon, aluminum-silicon, and calcium-silicon ratios averaged over large areas of the planet's surface show that, unlike the surface of the Moon, Mercury's surface is not dominated by feldspar-rich rocks. Messenger's gamma-ray and neutron spectrometer detected the decay of radioactive isotopes of potassium and thorium, and researchers have determined the bulk abundances of these elements. The inferred ratio of potassium to thorium is similar to that of other terrestrial planets, suggesting that Mercury is not highly depleted in volatiles, contrary to some prior ideas about its composition and origin. Messenger's Mercury laser altimeter has been mapping the topography of Mercury's northern hemisphere in detail. Previous Earth-based radar images showed that around Mercury's north and south poles are deposits thought to consist of water ice and perhaps other ices preserved on cold, permanently shadowed floors of high-latitude impact craters. Messenger's altimeter is measuring the floor depths of craters near the North Pole. The depths of craters with polar deposits support the idea that these areas are in permanent shadow. The geometry of Mercury's internal magnetic field can potentially allow the rejection of some theories for how the field is generated. The spacecraft found that Mercury's magnetic equator is well north of the planet's geographic equator. The best-fitting internal dipole magnetic field is located about 0.2 Mercury radii, 298 miles or 480 kilometers, northward of the planet's center. Researchers are assembling a global overview of the nature and workings of Mercury for the first time, and many earlier ideas are being cast aside as new observations lead to new insights. The primary mission has another 3 Mercury years to run, and we can expect more surprises as the solar system's innermost planet reveals its long-held secrets. The Carnegie Institution has had over 100 years of extraordinary discoveries. To continue this tradition, Carnegie scientists need your support. For more information about this and other cool science, visit our website at carnegiescience.edu. This is John Strom.